Right, we've got a worked example here for a quadratic model. This is in the modeling section. It actually it sort of uh, purports to be a linear model, but in actual fact, that's only part of it, and there is a quadratic model in there as well. Let's have a look. Unit price of an item affects its supply and demand. The price goes up, demand goes down. Yep. And a local newspaper has 84,000 subscribers at a quarterly charge of $30, and market research has suggested that if the price were 32, they would lose 5,000 subscribers. Assuming that the subscriptions are linearly related to the price, so we're assuming a linear model here for S and P, what price should the newspaper charge for a quarterly subscription to maximize their revenue? Right. Okay. Well, I think what we need to do here is what we really all need to do is look at the variables involved. We've got S subscribers and P price, but the gist of the question really is about revenue. Now, revenue, of course, is price times the number of subscribers. So we've got to work this into it somehow. Let's have a look first of all at the linear model. So here we go. We're assuming a linear model between a relationship between S and P, but as in these linear models, we have two unknowns, which of course, if we drew a graph of this would correspond to the intercept and the gradient. And we're given two boundary conditions. Now, what we've working subscribers in thousands here. So let's take S equals 84, then P equals 30. That's this first statement here. And then second one, they would lose 5,000 subscribers, though. So therefore, we're going to use S and P is 32. Okay, just check that against the problem statement, if you like. Now, we don't have an initial condition here. It doesn't really make sense in this context. So if we substitute these values into our general form here, we're going to get two equations in two unknowns. And that is typically what you're going to do with two boundary conditions and two unknowns. So we can resolve for those in the normal way, and we're going to get A equals 159 and B equals minus 2.5. These are all in thousands again. So the number of subscribers in 1,000. So that would be minus 2,500. So it's 2,500 we lose for every dollar. You'll put the price up. So our relationship is just this then. S equals 159 minus 2.5p subscribers price. Now, what price should the newspaper charge for quarterly subscription to maximize their revenue? Well, of course, revenue is price times subscription, as we've said. Now, since we've got subscription in thousands, basically this R is also in thousands of dollars. So we can write this, and of course S we kind of worked out to be that. So therefore we've got R equals this thing here, which we can factorize to this. Now this is a quadratic. There's no constant in here, but that doesn't kind of affect the model. And if what we do is we factorize and then complete the square, which is what we tend to do with these things. First of all, we take this minus 2.5 out, put that up front, and then what's left we actually complete the square on. Okay, so that gives us P minus 31.8 squared, and then of course we've got constant here because that's the we have to 31.8 squared, which we've had to subtract off. So that is the completing the square process. Now, so what conclusions can we draw from this relationship? Well, the first thing we can say is that the maximum value of the revenue happens when the price is $31.8, because at $31.8, this component is zero. The square of it is obviously zero as well. Now, if we move either side of 31.8, either slightly more, and this would be a small positive number, or below, that would be a small negative number. Either way, this term is going to be a positive number. And as such, its contribution to the revenue, when we take into account this minus sign here, is going to, well, reduce it. So, so that maximum reduction, if you like, happens when P equals 31.8. So it's a very common theme to these quadratic models. So, and then when this term is 0, or when the price is 31.8, the actual revenue is this times what's left in these brackets is minus 1011.24. Remember, we're talking in thousands here, of course. So that's it. That's our conclusion, really. The value of P that gives the greatest revenue is therefore 31.8. So that's 31.8 dollars. And the maximum revenue is given by minus 2.5 times minus 1011.24, giving us that. And of course, that being in thousands, then our maximum revenue is $2,528,100. So that is that. Now, it is a graph. This has obviously been drawn after we know what the parameters are, but this gives the idea of what's going on. This is our quadratic, our negative quadratic shape. And it's got this, its maximum here at 31.8 and the maximum value there. So that just helps to kind of illustrate what is happening as we increase the price. Okay, and by the look of this, by the time we get to about the price of $63, we've lost all our subscribers. Right. So that's it. Basically, I think that's kind of quite useful, but sort of brings out this idea of the quadratic model and its relationship to the linear model. And you know, one learning point from this, I would say, is, you know, let's recognize what the variables are in there, because that will give us a hint as to what we have to do. Great. Well, thanks for listening.